Okay, so hello everyone. Is my voice audible? Am I audible? Okay, thank you. Fine. So let's start today's lecture. So today's lecture will be mostly numerical based, more because we will be talking about normal stress, shear stress. I have added a little bit of future lectures also because the amount of questions being formed from this are very less. So let me start with the revision first of all, and then we can move forward. The things are basically more of a formula based, but we need to understand some of the typical concepts in which the questions can be formed from this part of the lectures. Okay, so let me start directly. So this is week number 4 of weekly numerical sessions for the subject mechanics of solids. I'm Samir Lavankar. Let's begin our discussion. Okay, so let's start with the revision first of all. So as in the lectures, the first I think 2 lectures or 3 lectures were basically depending on the previous tutorial questions only, which was already been completed in the previous lecture. So I will be starting with the new concepts which were being explained in I think third, fourth lecture of the this particular week. Okay. So first of all, the professor started with the introduction of stresses. We first need to understand what are stresses. So stresses are simply, we already know what is stress. So stress is defined as the limiting condition of an internal force. Please remember, it's an internal force. We are always talking about internal force segment as the area tends towards zero. So therefore, by definition, we can say that stress is nothing but limit delta A tends to zero, where delta is basically the very infinitesimal or very small amount of area delta F upon delta A. Okay, so this is stress. Now, what is stress vector? So you need to understand some of the new the wordings or the definitions can be new sometimes. There is a word which is called as traction. We will try to understand what is the meaning of traction when we will understand some of the questions. So you need to understand what is traction, you need to understand what is shear stress, you need to understand what is normal stress. If you understand all these terminologies, the particular questions will be much more clear. Okay, so let's not focus on traction for now. Let us understand what is stress vector only. So what is stress vector? So the stress vector Tn, the stress vector Tn acts on a specific plane passing through a point defined by its direction normal n. Okay, so as you can see in the figure, let us suppose that this is the particular body on which several external forces are being acted upon. These are the external forces which are being acted upon this body. Let us suppose we are slicing a particular semicircle, or let's say this particular section from this. When we'll divide this and we will see the internal part of this body, it would look somewhat like this. Now we are considering a point O up here. Now we are considering a point O here, through which we are trying to say that okay, there is a perpendicular vector which is called as normal vector being applied, okay, or being directed. This normal vector is not any application, it is basically used to explain the direction of the normal or direction of this area. Okay, so the vector which is perpendicular to this area is basically called as your normal vector. The basic use of normal vector is just direction. Okay, fine. So as you can see here, now you can see due to all these forces, if you would just let's say take F3 only, or let's say take F1 only, there are several different ways in which the direction can be implemented up here. That is being shown here. Okay, but we don't need to look like this. We just need to look at summation of forces. So basically, we will divide these forces into our 3 different directions. What will be 3 different directions? It will be x, y, and z. Okay, or in numerical form, vector form, we can say that to be I, j, and k. Okay, so for now we know. Okay, so a section is being cut, and a normal vector is being formed. Okay, now let us understand what is written here. So it's simply stating that the stress vector Tn acts on a specific plane passing through the point defined by its direction vector. Okay, so stress can actually act along this particular section. Now there are different types of stresses. Now we need to differentiate or dissociate these types of stresses. If we can understand each and every meaning of each and every stress, then actually the definition part is actually being crystal clear to us. Okay. So it is important to note that the stress vector does not necessarily act in the same direction as the normal vector. This is very important. Stresses can act in any of the direction. For example, As you can see from this figure also, this is acted in this direction, this is acting in this direction. There can be something in the plane also. Let us assume that this red area or this red arrow which I'm making is actually along the plane, and there will be somewhat, let us suppose, yeah, so you can see this one is actually along the direction of n. The stresses can act in any direction. Now, the stresses, when acted in some particular direction, some particular cases, are being actually defined by some terminologies, which we will be understanding in the subsequent slides. Okay, let's move forward then. First of all, let us understand the basic convention which is being implemented in mechanics of solids. Okay, so what is the convention? The convention for identifying the positive and the negative faces of a body in a coordinate system. Okay, so when we say a face is positive, a face is positive if its outward directed normal vector points in the direction of the positive coordinate axis. For example, as you can see here, the outward normal vector is in this direction. Okay, and it is a positive phase. Positive phase as in the phase which is towards, now means, let us suppose that this particular body is actually kept, it's one of the center, is one of the corners, what I say, are actually kept at the origin, then the phase which is far apart is basically called as a positive phase. Okay, which are actually at the origin, the phases which are actually at the origin are basically called as your negative phase. Okay, fine. So it is written here that a phase is positive. A phase is positive if the outward directed normal vector, is in the direction of the positive coordinate axis. So as you can see that it is along the direction. The direction is same for positive coordinate axis and the direction of normal vector to this phase. Therefore, the phase is called as positive. Okay, we will understand why we are trying to understand this definition or convention of positive and negative phases. Okay. Fine. Uh, next point is regarding negative phase. So conversely, a phase is negative if its outward normal vector points in the negative coordinate direction. Okay, so as you can see for the before part, if you see clearly, this direction will be in this direction, and because it is opposite to this x direction, therefore the phase will be negative. Fine. Okay, so this thing is clear. Let's move forward then. Next thing is basically regarding resolution of forces, a definition terminologies regarding the normal stress and shear stress. Okay, so here the lecture explains the fundamental concepts of stresses within the field of mechanics of solids. The discussion centers on defining the stress at a point by analyzing forces acting on internal planes within the body. This is a clear example of internal planes in the body. So we are actually basically dividing it into several planes, and we are taking into consideration one single plane for our complete understanding. Okay, so let us suppose we take this particular section for our understanding and try to understand how to resolve the forces, and second, how to get shear stresses and normal stresses. Okay, so basically after division we actually get this form in which, let us suppose that this is the section we are talking about and there are three different forces. So let us suppose there is just one force F in this direction which is acted upon. We can actually resolve it into three different directions. One is along the x direction, one is along the y direction, and one is along the z direction. Correct? Therefore, we can simply write that delta F is nothing but equal to delta Fx I cap plus delta Fx j cap plus, sorry, this should be delta Fy j cap, and this is delta Fz k cap. Okay, fine. So therefore, first of all, defining the planes and faces. So we basically understood that we are talking about what is basically positive x plane and what is basically negative x plane. The second thing is regarding the resolution of forces. So when a body is cut into segments, the resulting internal force delta F on a small area delta A can be resolved into three different components. Okay, one is all normal to the plane and the other two are basically parallel to the plane. So as you can see clearly, this delta Fx is basically perpendicular or normal to the plane, and delta Fy and delta Fz are basically parallel to the plane. Okay. Using after the resolution, we basically understand two different terminologies. One is called as normal stress. As the name suggests, normal stress is acting normal to the surface. Shear stress are the stresses which are exerting or basically applied parallel to the surface. Okay, so that is only the definition which is written here. First of all, normal stress denoted by sigma. is basically defined as the force component perpendicular to the surface. The notation represents stresses on the x plane acting in the x direction. Okay, stresses on which plane? On x plane acting in x direction. Okay, so in other terms we can actually write this as sigma xx. Okay, x plane x direction. Fine. Moving forward, what is shear stress? Shear stress is basically defined as the force component parallel to the surface. For example, denote the basically this tau. This is basically tau. Basically denote the shear stress on the x plane acting in the y direction. So we can write basically this to be tau xy. Okay, fine. So now we understand what is resolution of forces, why we resolve the forces, where are these forces actually acted upon, how to basically define normal stress, how to basically define shear stress. Okay, fine. Let's move forward. So next is now the state of stress at a point. So what is the meaning of this basically is that when you actually talk about this particular this particular value, each point on the particular body actually gets attracted upon or actually get exerted upon several amount of forces. In definition, there are 9 total stresses or 9 different resolution of stresses which are being acted upon at point O. Okay, that is the first definition which we need to understand, and hence the particular subsection. Okay, so the state of stress at a point. So by considering three orthogonal planes x, y and z, orthogonal as in they are 90 degrees to each other, passing through a single point, the lecture demonstrates that 9 stress components are required to define the full state of stress at that point. These are typically represented in a matrix. Okay, so basically how we basically define this? So sigma at a point is basically defined in terms of a 3 cross 3 matrix. Okay, one is first is regarding sigma xx, second normal is sigma yy, third normal is sigma zz. Similarly for shear stress, it is tau xy, this is tau yx, right? Then there is tau zx, then there is tau zy, and this is tau yz, and this is tau xz. Okay, so these are basically 9 different stresses which are actually acting upon a single point only. Okay, fine. Let's move forward. Notation and mapping. So we basically understood that either we can actually use sigma ij form, or let's say if we know that sigma xx is actually along x direction, to reduce time, to reduce the multiple methodology in which we try to write xx again and again, we can simply use sigma x. For sigma y we can directly use sigma y, and sigma z we can directly use sigma z. Okay, fine. So that was regarding this, and finally I think this is the last thing. Yeah, so definition of plane stress. So basically a state, what is plane stress condition? Or there are two different conditions which major of the problems in mechanical solids are being explained upon. One is called as your plane stress condition, and second is your plane strain condition. Okay, for now let us understand what is plane stress. So in plane stress, a state where stress exists only within a single plane. For example, the xy plane with no variation in the z direction. That means there is no stresses or very minimal stresses which are acting upon in the z direction. So therefore we assume that the amount of values are approximately or tending to 0 only in z direction. Okay. So when we do this, our 9 total stresses actually gets converted to only 4 stresses. Okay. For the stress components, while the 3D state involves 9 components, plane stress reduces this to 4, that is sigma x, sigma y, tau xy, and tau yx. Okay, so we basically write this in the form of sigma is equal to sigma x, sigma y, tau xy, tau yx. Okay, fine. Next is regarding the sign conventions. The sign convention will be much more clear when we will try to solve some problems regarding this. So let's not look much forward to it for now. It basically tells that we will basically emphasize regarding negative and positive stresses, emphasizing that tensile normal stresses are considered positive. Okay, so tensile is basically considered as positive, and compression is basically considered as negative. Okay, and the final thing which we need to remember regarding from the chapters is that you need to understand that cross shear components are always equal. What does it mean? It basically means that your tau yx is basically equal to this form. This is basically tau yx and tau xy are equal. Similarly, tau zx and tau xz are equal, and similarly tau zy and tau yz are equal. Okay, fine. And similarly from here also we can simply state that tau xy is basically equal to tau yx. Okay, so I hope this thing is also clear. Now let us move forward to solving some problems. Before you try this problem, I need to explain a little bit from the future lectures also. So basically to solve some of the questions regarding different stresses we have acted upon. So what is our main motive? Our main motive, yes, you can say. So basically what happens in plane stress condition, as you can see here, plane stress. Plane stress basically means that the amount of stresses in sigma z direction is approximately equal to 0. These are which are called, which are what are defined as plane stress condition. In the lecture also, if you remember, plane stress condition are basically explained when, let us suppose that this is one sheet of paper. So when you try to actually expand it, let's say apply tensile stresses into it, the amount of stresses which are actually exerted upon in z direction are very, very less. Such forms of questions in which not such forms of questions, such forms of materials in which the application of stresses are acted upon in this way are basically explained or modified into plane stress problems. So they are basically called as plane stress conditions. Similarly, what happens in plane strain is that the amount of strains in z direction is basically denoted as 0 or approximately equal to 0. So when does it happen? It basically happens when the amount of length along one direction is infinitesimal, or we assume it to be infinitesimal. So those are basically called as plane strain problems. Plane strain problems examples can be, let us suppose you are actually trying to understand or trying to model a material which is having infinitesimal length. For example, a slope, or for example, an embankment for a railway model, or for a railway, let's say railway, what we can say, rail lines. So in that way, we cannot actually model the complete infinitesimal length. So we assume that the direction in z direction is approximately 0, and we assume it to be a single model is 2D direction. That is the basic definition between plane stress and plane strain. So I hope this thing is clear now. Okay, fine. Okay, thank you for asking. Okay, fine. So let us move to the first problem. Before moving to the first problem, I will just explain you the agenda of solving all these questions. The main understanding of all these questions is basically to understand the next concept, which is regarding the Mohr circle. Before going to the Mohr circle, we will try to understand each and every aspect of resolution of forces, what is actually acted upon. For example, in the previous diagram, we actually understood that okay, we cut a particular section from this and we try to understand it in this form, but the stresses are actually being resolved in only three directions: at delta fx, delta f, and delta fz. There will be several different forms in which the resolution of vectors can actually happen, and that is the basic definition, or that is the basic turning point at which we try to actually define more terminologies to understand mechanics of solids much more clearly. For example, principal stresses, for example, principal strains, for example, maximum shear stress, for example, in plane shear stress. So our main motive should be to understand each and every word crystal clear, so that what if someone asks, if the questions in the exam is being asked, try to find out the maximum in plane shear stress, then we should actually understand what is the meaning of in plane shear stress, what is the meaning of maximum shear stress. Generally people confuse when the questions are being asked, find the maximum shear stress, find the maximum in plane shear stress. So our aim for this lecture is to be very, very well versed with all the calculations which have been performed for the resolution of forces, or basically to calculate, let us suppose, principal stress directions, or let's say that angle, sorry, the forces acted upon at a particular angle. Okay, so before starting the lecture, I will just write a few formulas which are being important. Those formulas will be derived at a much more greater clear extent when the professor explains it in the subsequent lectures. But for now, I will just write the formulas here. Okay. So basically we will be using 3-4 different formulas. One is regarding, first of all, we should know what is sigma average. So sigma average, major of the questions will be based upon your plane stress conditions. Okay, so we only assume that we are understanding all the things in a 2 cross 2 matrix, in which we are having sigma x, sigma y, tau xy, and tau y. Okay, so basically sigma average is nothing but sigma x plus sigma y by 2. Okay, then there is something called as d. We define d by our own means. It is not a necessity, but just to simplify the formula, d is basically sigma x minus sigma y by 2. It is also called as center of the Mohr circle, but I don't want to explain or add anything from the future concepts. Next thing is regarding sigma x dash. Sigma x dash is basically the stress acting in the x direction but oriented at some particular angle, theta. Okay, how we calculate it? Sigma x dash is basically sigma average plus capital D cos 2 theta plus tau xy. Tau xy is basically the shear stress acting on that particular plane, parallel to the direction, or basically perpendicular to the direction of normal vector. Okay, sine 2 theta. Similarly, what is sigma y dash? Sigma y dash is again the stress acting in the y direction but at an angle theta. So sigma average at an angle theta to the sigma y. So basically, if some sigma x and sigma y is given to you, but you don't want the direction, but you don't want the stresses in that particular direction. You want the stresses at some particular another orientation. Why do we need another orientation? We will get to know when we will go past the lecture. But for now, let us assume that we need to understand or need to know the forces at some particular angle theta. Then sigma y dash is basically sigma average minus d cos 2 theta minus dxy, sorry, tau xy sin 2 theta. Okay, similarly, yeah, sure, tell. Okay, just fine. Okay, give me just 2 minutes, I'll explain. Fine, so these are basically regarding the stresses. Then next is regarding the explanation of sigma 1 and sigma 2. Sigma 1 and sigma 2 are basically the maximum principal stress and the minimum principal stress. The meaning of maximum principal stress basically means that a plane, or basically an orientation of stresses, such that the shear stress acting along that particular orientation is basically zero. So when the shear stresses are zero, sigma 1 and sigma 2 are calculated. Those are basically the normal direction forces, normal stresses, not forces, normal stresses, which are basically denoted as sigma 1 and sigma 2. Okay, so what is sigma 1? Basically sigma 1 is sigma average plus r, and this is sigma average minus r. Okay, where what is r? R is basically sigma, sorry, this is root over d square plus tau xy square. Fine. And to know the angle of orientation of this, tan 2 theta p is basically 2 tau xy upon sigma x minus sigma. Okay, so we will be majorly using all these formulas in our complete lecture today, which are basically based upon orientation of stresses in a particular direction. Okay, fine. So now to explain whatever you the thing you asked, so let us suppose we are actually taking one section up here. In particular sense, sigma average does not have any superficial meaning in sense of what you are trying to elaborate or what you're trying to understand. You won't get sigma average at any particular location. There will be one point, at which sigma x plus sigma y by 2 will exist. But the major use of sigma average is just to calculate the principal stress directions. As you can see, principal stress directions are basically hovering around sigma x plus r or sigma x minus r. There is a concept which we will understand in subsequent lectures regarding Mohr circle. So what is actually Mohr circle? Mohr circle is basically used to find out all the different stresses which are acting upon that particular point, but at different orientations. So when you try to rotate the orientations at which you try to want to calculate the value of sigma x, sigma y, and tau xy, or basically sigma and tau, you actually get different values. Okay, so if you actually try to understand from that response, you can get that sigma 1 is actually residing here and sigma 2 is actually residing here. So sigma x plus sigma y in one form can be that it is actually one value of stress. That is the only meaning which sigma average can actually have here. I hope this thing is clear now. Yeah, yes, yes. See, sigma average is not a vector quantity up here. Sigma average is a scalar here. We are trying to find out some scalar quantity. In one way, sigma x and sigma y does not denote vector direction because it's very simple. Sigma x is actually acting in y direction. Sigma sigma y is actually acting in j direction, right? Any stress which are actually acting upon in two different directions, if you actually try to add them up, it won't be actually acting in either I, either j. Okay, it will be acting upon in this direction. Sigma average is just a term. It's just a term or basically a value which is being defined in the mechanics of solids to denote a scalar quantity so that we can actually get the magnitude of sigma 1 and sigma 2. In general sense, sigma x plus sigma y by 2 doesn't mean that it is actually some stress which is being acted upon in some direction. It's very correct way of saying that, yeah, sigma x is actually acting in I direction, sigma y is actually acting in j direction. How can it actually define some stress? It is not defining some stress. There is a clear difference between what is a scalar, what is a vector. Sigma x is a scalar. We are just trying to find out some different, it's just an approach to finally reach sigma 1 and sigma 2. Sigma 1 is actually acting in some direction. Sigma 1, for calculation of magnitude, we actually explained this complete procedure and finally obtained this particular final formula, sigma average plus r. Sigma average plus r, the magnitude of that vector is actually this, but a direction is in the one direction. What is one? One is basically that particular orientation. Okay, sigma average is scalar. Sigma average does not denote a vector quantity. I think you are trying to, or basically somewhat confused in a scalar quantity magnitude and a vector quantity. Sigma x is in I direction, sigma y is in j direction, but the average is not, average here is not telling you about anything regarding magnitude, sorry, direction. It is only telling you about the magnitude. These are only the different ways in which we try to understand how we can actually approach the final orientation or basically the final principal stress direction. If a question is being asked, say. Okay, say, please say. Yes, 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 exactly. Yeah, yes, yes. So, like for example, if some, as you said regarding sigma x and sigma y by 2, someone can say about sine theta and cos theta also. Like why, if particular thing or if particular force is actually acting upon in this direction, let us suppose, why we are taking f cos theta, and how can f cos theta can actually go in x direction if f is actually going in some value orientation, let's say if it is 45 degree. We are trying to use cos theta as our approach as our approach to actually find out the magnitude of this force in the x direction. Cos theta doesn't have to do anything with direction. I hope you try to find out the analogy between f cos theta and sigma x plus sigma y by 2. F cos theta is just a scalar term. It's just the magnitude of the term of f in x direction. Similarly, sigma x plus sigma y by 2 is just a term. It is just a terminology which is being used to finally calculate anything. For now, we are trying to calculate principal stress directions, or principal stress magnitudes. Similarly, cos theta is basically used to find out the resolution of force F in x direction. Okay, we are trying to find out some scalars which will actually use, or which will actually advance us to find out some complex vector quantities. Is it clear? Fine, thank you. Okay, so now please just use these all formulas and try to solve the first question. I will help a little bit regarding this. So as you can see in the question, sigma x is given to you. We will try to understand the actual meaning of all these things, because if we understand the meaning of all these things, when the questions regarding Mohr circle or the future concepts come, we are not hesitant regarding all these concepts. People confuse when the questions regarding maximum in plane shear stress, maximum plane shear stress, principal stress direction, orientation in one direction relative to another direction, when this terms sort of terminologies comes in paper, people actually get confused. So we'll try to understand each and every point as far as this numerical session is being considered. Okay, we'll try to strengthen up our numerical portion, calculation portion, and try to understand actually what is happening, what is sigma x dash, why we are trying to put it at some orientation, what will actually happen, and so on. Okay, let's start with the first question and then we can actually solve further questions. Okay, so fine. So sigma x is basically given as 85 MPa. So let's make very basic model. Uh, let us suppose we are talking regarding these all concepts. Let us suppose this is the section we are talking about, and this is very infinitesimal point. Okay, I am trying to scale it big, but assume it that it is very small area on which the stresses are being acted upon. Okay, so it's basically a point, but we are actually defining a point in some particular area. Okay, okay, fine. So let us suppose sigma x is basically acted upon in this direction. So this is sigma x given to us. Sigma y is basically minus 35. Understand the meaning of minus and plus here. Sigma x 85 basically means that it is tension. Okay. Sigma y of minus 35 basically means that it is compression. So it is basically trying to compress this particular plane. Okay. And tau xy as 48 is basically shear stress is actually acted or directed like this. Shear stress is basically the stress which is acting along the plane. Okay, so it is trying to shear it. Tau xy is basically 48 mm. Okay, and now some theta is also given to us. Okay, the question asks is basically to find out the values of stresses sigma x dash and sigma y dash and tau xy dash, which is being acted upon at some particular angle theta, which is 32 degrees. Okay, so what does this mean? This basically means, again, the stress sigma x dash also acts in x direction only. Sigma y dash also acts in y direction only. But now the orientation is basically being changed. So this is the plane up here. Now we are basically trying. Now the plane is actually a point only. Now the point can be actually be visualized from any of the directions. Let us suppose the original point is being obtained. Let us suppose this is that point, and we are trying to understand this point from theta is equal to 0. Now we are basically saying that okay, this is that plane. Let us rotate this plane. Let us rotate this plane. Now, if it is infinitesimal, rotating that plane won't make sense in a much bigger substance. But when we are actually trying to understand it at a very infinitesimal eyesight, then basically this plane is rotated at 32 degrees. Now, if it is rotated at 32 degrees, sigma x dash is the plane which is perpendicular. Understand this very carefully. Sigma x dash is the plane which is normal to the direction. Sigma y dash is basically the plane which is perpendicular to x. And tau xy is the plane which is actually acted upon in plane of the shear, on the plane. Okay, try to understand it in 3D, because understanding it is in 3D is very important when we actually go from plane stress to real life conditions. So we'll try to generalize each and every point and try to move forward. Okay, I will explain again. So basically, let us suppose that this is that orientation we are talking about. We are actually rotating it by theta 32 degrees. And now when we have rotated it, we are trying to find out what is the value of sigma x dash, sigma y dash. So basically one is sigma x dash in x direction, sigma y dash, and one is regarding the plane. Okay, I hope this thing is clear. Now let's try to solve this. Okay, so please just solve sigma x and sigma y dash using this formula and give me the answer for this. Use theta to be 32 degrees. The derivation of these formulas will be explained in the subsequent lectures, how these formulas came. Okay. So this is a much better approach to understand what is actually happening here. So this is basically the normal plane which is on which sigma x, sigma y, and tau xy is given to us. I've actually designated sigma y as compression and sigma xx as tension as it is given in the question. And this is actually the orientation theta is equal to for 32 degrees. Okay. So basically, as we are actually assuming this to be a very infinitesimal point, so that infinitesimal point can actually rotate in the particular sequence. But when we actually rotate it, the actual sigma x dash and sigma y dash changes. We need to understand this. Try to understand this on the actual deep root level, what is actually happening inside. Okay, there can be several instances in which sigma xx in particular orientation can be positive, but at some orientation it can actually go to negative. Okay, that is the main essence which we are trying to understand from this from this weekly session. Okay, you need to understand what is actually happening inside. So basically, rotation of a particular plane leads to the value of stresses acting upon to go from compression to tension also. Okay, fine. So let me also write. So basically, how to do it? As simple. For this, so everything is written here only, so there is nothing to worry. But you need to remember all these formulas. So sigma average is basically sigma x plus sigma y by 2. So when you will calculate it, you will get the value as 25 MPa. The next is regarding the value of capital D. That capital D value is nothing but equal to 60 MPa. Okay, and 2 theta is basically 64 degrees, correct? So when you will just put these values, you will get sigma x dash is basically equal to 94.44 MPa, and sigma y dash is basically equal to minus 44.44 MPa. So here you can now actually calculate or basically differentiate. You can see the sigma x value has actually increased, and the value of compression is also actually increased, but the point was same. So it basically depends upon the orientation from which we actually visualize the complete situation. Sometimes the analysis or visuality is also important. Let us suppose you are an engineer and you have actually designed something using only these stresses, and what if these are the stresses which are actually coming at the particular point only, but we neglected this. Then neglecting these quantities will lead to the failure of that substance. That's why we are trying to understand this. Next thing, we will understand principal stress direction. When we understand principal stress, we will see that the value are actually much more than this. Okay, so that is the main reason why we try to understand all these concepts in mechanics of solids. Our main aim is that, okay, if you are an engineer, you need to find out at which particular stresses something fails in normal and something fails in shear. If you understand these concepts very, very carefully, you can actually design the materials at a particular instance if which you require. There are several quantities which actually fails in shear at a very lower rate, but actually fails in normal at a very higher rate. You can actually visualize what is happening inside for a material which is for a very, very small infinitesimal value. Now, if only shear direction strength is required to us, we will create a design in which the shear strength is being obtained very, very high. But if we require for both, then we need to design at somewhat different pace or with some different understanding. That is the main essence of trying to understand these different stresses which is acted upon. Okay, so that was just for some general gist why we try to understand what is the main reason we need to understand all these concepts in mechanics of solids. Fine. So sigma x dash is known to us, sigma y dash is known to us. Similarly, we can get tau x y dash and tau x dash y dash. So for tau x dash y dash, when you will put the formula, you will get this to be minus 32.89 MPa. So if you see very, very carefully, the direction of shear stress has actually changed. Okay, first it was positive, the second it is negative. Okay, so this is also very, very important. We need to find out the reversal of shear stresses also. There are several quantities, there are several not quantities, there are several materials in which the reversal of stresses is a very, very destructive phenomena. Several engineers try to understand or basically do research on reversal of stresses, how to remove the reversal of stresses, why does removal of stresses happens. When you will actually design or when you will actually see many of the, let's say, railway structures or let's say steel structures, reversal of stresses is very, very destructive thing which we need to have, which we have to keep in mind. For example, you have actually designed something for positive shear stresses, but let's say reversal of stresses happen and negative shear stresses happen in picture. Then what you will do, the complete model is fake, is not of use to us. That's why we need to make sure that the complete model or the complete design of, let's say, bridges or let's say any steel structures are actually being comprised or actually being understood in both the tensile and the compressive phases. Okay, so these are just some of the instances where these all concepts actually work upon. Fine. So we have actually calculated what is sigma x dash, what is sigma y dash, and what is tau x dash y dash. Next thing is regarding principal stresses. Okay, what is the meaning of principal stresses? The principal stresses are those maximum value of normal stresses at which the shear stress is zero. Okay, that is the most basic meaning of principal stress. There are several different definitions based upon the complexity involved, but for your understanding you can simply assume, you can simply understand the principal stresses as those normal stresses acting upon at some particular orientation such that the shear stress value is zero. Okay, what are principal directions? Principal directions are basically the directions of the principal stresses. Okay, so let us assume that we are assuming this to be at theta equal to 0. Then theta equal to 0 is in that for theta equal to 0, x direction is actually the x direction, y direction is actually the y direction. Okay, let's not get confused at any of the points. Okay, theta 0, at theta 0 what will happen? And you will actually find out the stress in sigma x direction, that will be in x direction, and sigma y will be in y direction. But for any other orientation, sigma sigma x will get converted to or transformed to sigma x dash. Therefore, these equations are also called as transformation equations. Okay, fine. So there will be some value or some orientation of theta at which tau x dash y dash will come out to be 0. The orientation at which it will come out to be 0 are basically 2. Okay, we will understand you will get to understand why they are 2 in subsequent lectures when you will understand, I think week 5 or week 6. But for now, let us understand this from this perspective only. So basically, principal directions are those directions at which principal stresses act upon, and there are two different it has two different values, sigma 1 and sigma 2. So sigma 1 is basically called as maximum principal stress, sigma 2 is basically called as minimum principal stress. Okay, fine. So calculating sigma 1, how to calculate sigma 1, you actually know the formula for now. You will get the essence much more clearly in the subsequent lectures when you will understand week 5 or week 6. Okay, so yeah, yes, you say. Minimum principal stress basically means, let us suppose you are actually this is the particular section, this is the particular section, this is your x direction, this is your y direction, and this is your z direction. As it is a plane stress condition, there is nothing acting upon in z direction, so we will ignore it. Okay, so let us suppose this is your x direction, this is your y direction. Okay, so now as a very basic engineer which is trying to understand what actually happens when you keep on varying the value of theta. Okay, you start with theta equal to 1, you go theta equal to 2, theta equal to 3, and you keep on rotating till theta is equal to 360 degrees. Then you will go start from 0, go to theta equal to 360 degree, put all the values of here, you will get different value of sigma x dash, sigma y dash, and tau x y dash in some this sense. Okay, let us say we are going from 0 till 360 degrees. You will get some value of sigma x dash, you will get some let me erase this, you will get some value of sigma y dash, you will get some value of tau x dash y dash. I hope it is clear till this point. Now there are just two different instances at which the value of tau xy is 0. Okay, the two instances at which tau xy are 0, when you will actually calculate it using theta 0 to 360 degree, you will actually get one way. Let us suppose, for example, I'm assuming this value, it is 120 for now, let us assume magnitude wise it is 120, and sigma y you got minus 60. Okay, another way when you will get it again is again 120 and minus 60 only. Okay, so when you will actually get it, we say that the maximum value which you get for sigma is basically your sigma 1, and the minimum value which you get is basically sigma 2. This is the meaning of sigma 1 and sigma 2. So sigma 2 can be positive also. The magnitude as in see, there are means the confusion can be from magnitude also. Sometimes we say something to be magnitude wise always positive, and there is something called as absolute. Okay, don't look at absolute quantity, look at the magnitude as a magnitude of vector. Okay, so the magnitude of sigma 2 can be positive also, can be negative also. Similarly, sigma 1 also can be positive, can be negative. Okay, but when we try to compare sigma 1 and sigma 2, the value which is on the higher side is basically defined as sigma 1, and which is on the lower side is basically defined as sigma 2, irrespective of the sign. Okay, I hope this thing is clear now. You may ask if you are unclear till now also. Okay, fine. Fine. So basically, what is sigma 1 now? So when you will calculate sigma 1 is basically when you will calculate the value, you will get this to be 101.84 MPa. And similarly, sigma 2 is basically minus 51.84 MPa. Try to understand this very, very carefully. Okay. So what does it mean? I will try to explain it visually also. So you know that at theta equal to 0, this was happening. Let us first of all find theta p also. Okay. So when you will actually calculate theta p, tan 2 theta p. What is the meaning of tan 2 theta p? Tan 2 theta p, theta p is the orientation of principal stress. But we know that there are two different principal stresses. That means there will be two different orientations. Okay. So theta, tan to theta p is basically, this is just math. So you will actually get theta p as two different values. One theta p1 you will get 19.33 degrees, and another which is theta p2 is basically 109.33 degrees. Okay. Now we'll try to visualize the situation to you. Okay. So what is actually happening? This is the original situation. Okay, this was the x direction, this was the y direction. Okay, when you rotated this by theta, which is actually 19.33 degrees, okay, you got the value of sigma x dash as 101.84 ampere. Sigma 2 you got in compressive direction as minus 51.84 ampere. Tau x dash y dash you got as 0. When you rotated more till 109.33 degrees, again you got sigma x dash, sigma y dash as 101.84 and minus 51.84. Tau x dash y dash to be 0. That this is the basic meaning of principal stress. Principal stress, or in some another way, if I try to explain some another way, if you go by mathematical sense, you start from 0 degree, go to 360 degree, actually find out the value of sigma x, sigma y and tau x dash y dash. Okay, the maximum value which you will get in this particular columns is basically sigma 1, and the minimum value which you will get in this particular column will be sigma 2. When you will get this value of sigma 1 and sigma 2, if you look on the particular value of theta, that particular theta is actually your theta p1 and theta p2. Okay, I hope these things are clear till now. If it is not clear, you can even ask now. Yeah, yes, okay, okay. Wait, you are telling that there are two different stresses. Tell me the values of stresses again. What are the stresses? Okay, okay, fine, okay. So, see, sigma 1 and sigma 2 now will also be these only quantities. Okay, what you need to do is basically try to understand this in the number line. In the number line, which is actually acting on the rightmost point, that is your sigma 1, and which is actually acting on the leftmost point, is basically sigma. Yeah, you need to consider. Yes, yes, yes. That's why I was explaining regarding the app. Don't understand anything by absolute quantity. Understand by absolute, as in you understand na, that we write the absolute value. Absolute value of minus 51 is 151. Mod value, we say mod of something. We don't need to understand anything by mod value. We need to understand by its original value. Original value in terminology, we say it to be absolute value. Okay, so the absolute value. Okay, so now I hope this thing is clear. Anything, the value anything, you just need to look at the number line. Okay, by number line, whatever is acting on the rightmost point, that is denoted as 1, and what is on the leftmost point, that is denoted by 2. Okay, fine, thank you. Okay, fine. So I hope, so the first question is clear to us. We have actually calculated sigma x dash value, we have calculated sigma y dash value, we have calculated sig tau x dash y dash value. We understood what is principal stresses, we understood the magnitude of it, we understood principal directions, and now the only thing remaining is stress trace invariant. Okay, this is a very uh, interesting thing. I will just explain what is stress trace invariant. Stress trace is basically defined as sigma x plus sigma y. Okay, so the stress trace invariant, the word invariant means it does not vary. It simply says that sigma x plus sigma y is basically equal to sigma x dash plus sigma y dash is basically equal to sigma 1 plus sigma 2. That means the at any of the orientation, when you actually add the trace, what does it mean by trace? Okay, so when we actually understand the concepts of matrices, let us say if it is A1, this is A2, this is A3, this is A4. So this particular quantity, the diagonal terms, the summation of the diagonal terms is basically called as trace. So from there the word trace comes into picture. Okay, so we know in the plane stress condition what is the denotation of sigma. Sigma is basically denoted as sigma xx here, sigma yy here, tau xy here, and tau yz here. So this is again the trace up here, correct? So when you actually calculate trace of the stress quantity, it is sigma xx plus sigma yy. Now we know that sigma xx and sigma yy can actually be written as sigma x plus sigma y. Okay. So now when it was found that stress traces are basically invariant in nature. Okay, we can actually define it also. So when you will calculate sigma x plus sigma y, calculate sigma x plus sigma y, you will get the value as 50. And you will calculate sigma x dash and sigma y dash, you can again get this to be 50. And when you will get sigma 1 plus sigma 2, this is sigma 1 and sigma 2, you can again get it to be 50. Okay, so this is one of the interesting terminologies of mathematical consequence which actually comes into picture in stress trace invariant. Okay, so some questions can actually be solved using the concept of stress trace invariant also. Let us suppose you know sigma x and sigma y and you know sigma 1, and sigma 2 can directly be calculated. You don't need to use the formula of sigma 1 and sigma 2, calculate sigma average, calculate r, and so on. You can actually calculate it directly using stress trace invariant. Okay, fine. So I will just put it somewhere here only so that we can go with the next question. Fine. Now let us move on to the next question. The next question says that sigma x is given to you. Now you need to understand whenever these terms comes into picture, whenever the question asks as sigma x, sigma y, tau xy, immediately the picture of a square with sigma x going in this direction, sigma y going in this direction, and tau xy should come into your picture. If it comes into picture instantly, the questions to be solved in subsequent lectures are very, very simple. Okay, fine. So sigma x is given to you, sigma y is given to you, tau xy is given to you. The outward normal is given. Understand this. Outward normal is at theta is equal to 37 degrees. Okay. This has nothing to do with the orientation we are talking about in the previous question. Okay. These all values of theta actually confuses students. So that's why I try to keep all these questions so that all the confusion gets clear here itself. So that it does not get forward to subsequent lectures. Okay. Here we are talking about the outward normal is that theta is equal to 37 degrees. Okay. So find the traction vector. Okay, so first of all, I need to explain to you what is a traction vector. So first of all, let me write this. So in vector terms, we need to understand all these terms as in vector terminology. Okay, so when we write sigma in vector terms, how we can write it? Sigma x is basically sigma x, sigma y, tau xy, tau yx. Okay, I won't solve. I will leave the calculation part to you. And what is n? N is basically a normal vector. Normal vector is basically cos theta, sin theta. Okay. Now traction. Traction, as I already explained, traction is basically a terminology. Terminology, traction is basically defined as sigma dot n. Okay. Sigma dot n. You may ask what is the use of traction vector? Traction vector is basically used to calculate the normal stresses and shear stresses. How it is used to calculate, I will just put up till that portion and then leave it to you. So sigma is basically sigma dot n. Now sigma dot n will give you traction, but sigma n, that is normal stress, is basically tau dot n. Okay, dot product. And similarly, what is shear stress? Shear stress is basically T dot m. What is m? M is the vector, direction vector perpendicular to this normal vector. Okay, it is perpendicular to normal vector. How to calculate m in for this instance? It is actually calculated as minus sin theta cos theta. Fine. So that is the basic meaning of traction. This is how you calculate your normal stress. and this is how you calculate your shear stress. Fine. So please at least solve this question and give me the values of T, sigma and tau, and then we can move forward. Okay. So I hope you understood this. So basically what we are trying to understand up here is basic meaning of traction vector and what is the use of traction vector. Traction vector is basically used to calculate the value of normal stresses and shear stresses. Okay. So basically the plane was again given to us. The plane was given to us. The normal vector to this plane was given to us, but the orientation theta 37 degree of this normal vector with xyz with xyz is given to us. Okay, the normal vector is at theta is equal to 37 degree. Okay, so you need to understand that normal vector orientation with let's say x equal to 0 is given to us. Okay, fine. So that was the concept which I need to explain from this. Please calculate it and then we can move forward. So So this is the actual meaning of traction in a 3D space. So I hope some sort of visuality is clear to you. So traction was basically acting upon this direction, and then when you actually resolve for the particular area on which we are working upon, sigma n and tau n is actually calculated. So first resolve was for traction to come into this instance, and the second resolve was for t to actually denote in t sigma n direction and tau n direction. Okay. So that's how we actually approach this situation. Okay. Okay. So here I will just give the values. So t is basically I will when you will input it, you will get the value as 120. Then it's minus 55. Then it's minus 55, and this is 40. Then tau is basically cos theta sine theta. So I will just for now I'll write cos of 37 degrees and sine of 37 degrees. So when you solve this, you can simply get Tx. Tx is in the first I cap and j cap, correct? So it is nothing but 120 cos 37 minus 55 sine 37. That will give you the value as 62.74 MPa. And similarly, Ty is nothing but minus 19.85 MPa. Okay, so now you have Tx and Ty with you. Now you can calculate what is T. T is nothing but Tx I cap plus Ty j cap. Understanding of vectors are very important. Understanding of resolution of forces are very important as far as mechanics of solids are considered. If you have very good grasp of understanding what is x, what is y, how to resolve the forces, okay, it will be cos theta into cos theta, it will be cos theta into sine theta, then major problems, major complex problems are very easy for you. Fine. So we have T. Now similarly we can get sigma n. Sigma n is basically T dot n. So when you will get calculate T dot n, it is nothing but 38.16 MPa. And similar T dot m, for m you can directly use minus sine theta into cos theta. So when you will solve this, you can get simple value of minus 53.61 m. Okay, fine. So I hope this thing is clear. What is remaining? So we have calculated traction vector, we have calculated normal stresses, we have calculated shear stresses, we have calculated traction. Traction magnitude is nothing but under root of traction magnitude. Here the meaning of magnitude is different. Okay, so we are actually calculating the magnitude of traction. Okay, because it is a vector, so it is nothing but root over tx square plus t by square. Okay, so when you will solve this, you can simply get the value as 65.80 MPa, and the angle between traction and normal and the principal stresses direction. Okay, so angle is nothing but you can calculate the angle as let me add one more page. So we have mod t is nothing but equal to 65.80 MPa. Okay, and psi I have denoting it by some another sense, cos inverse sigma n by mod t. Okay, so these are very simple equations of vector only. I'm not deriving anything new. These are very small simple definitions of vector. So when you solve this, you will get the value as 54.56 degrees. Okay. Now, if you have sigma x and sigma y, so if you don't even need all these values which are being given here. If you have sigma x, tau xy, sigma y, you can actually calculate the values of principal stresses directly. Okay. So I will just solve this up here. So what is sigma 1 and sigma 2? Sigma 1 is basically sigma average plus r, where sigma average is sigma 1, sigma x plus sigma y by 2, and r is root over sigma x minus sigma y by 2 whole square plus tau x y square. Okay, so when you will solve this, you will get sigma 1 as 148.01 MPa and sigma 2 as 11.99 MPa. Orientation, you will get theta p1 by using tan 2 theta p. So theta p1 is nothing but minus 26.99 degrees, and theta p2 is basically 63.01 degrees. As it is in negative sense, in another way we can actually multiply, add 180 and write it equivalently equal to 153.01 degrees. Okay, it's the same thing. Okay, so one principal stress is acting upon in 148.01 MPa and another is acting at 11.9. Okay, fine. Okay, so that was the second question. Let's move to the third question. Okay, fine. So please solve this question till this point. Calculate sigma y dash, tau x y dash, sigma y dash, and then we can understand what is maximum influence shear and its orientation. Okay, so this is a new thing which has came in uh, this question number 3. Okay, please solve this till this point and then we can move forward. So in the first question, we basically understood the orientation concept, in which we understood how to calculate sigma x dash, sigma y dash, tau x y dash. We understood about the principal stress direction, sigma 1, sigma 2, orientation of sigma 1 and sigma 2, understood the essence of it. The second question was basically based upon the concept of traction. We understood what is traction, how to calculate sigma n and tau n based on traction, what is the orientation of sigma with tau. We understood again the principal stress orientation, principal stresses. Okay, the third question is majorly based upon a new thing, which is maximum influence shear. Okay, a simple quantity only, nothing typical, but we need to understand, but we need to know what is maximum influence shear. Okay, so please solve till this point. Please give me the value of sigma y dash, tau xy and sigma y dash, and then we can move forward. Understand, we are actually under the question asks about sigma y also and sigma y dash also. Okay, if you understand the meaning of sigma x, sigma y dash in this particular point only, the subsequent lectures are very easy, because people make confusion in this thing only, majorly. Fine. So if you look on the first and the second equation, you have two equations and you have two unknowns. When you will solve this, you can directly get the answer. Sigma y is 101.60 MPa and tau xy is basically 26.96 MPa. Okay. Now, second question asks this regarding sigma x is known to us, sigma y is known to us, sigma y is sigma y dash. Now, one way to calculate sigma y dash is put everything in this formula, and actually calculate it. Or another sense is we can directly use the trace invariance. Okay, so when you will use trace invariance, can simply get sigma x dash plus sigma y dash is basically equal to sigma x plus sigma y. You know all the values, you just don't know the value of sigma y dash. So you can calculate sigma y dash is basically sigma x plus sigma y minus sigma x dash. So when you will put the values, you will get the value as 71.60 MPa. Okay. So now this thing is also known to us. Next thing is regarding the principal stress. So sigma 1 is basically sigma average plus r. Sigma 2 is basically sigma average minus r. So when you will calculate it, sigma average plus r is basically 118.37 MPa. Sigma 2 is basically sigma average minus r, which is 58.24 MPa. Okay, next thing is regarding theta p1 and theta p2. What is theta p1? Theta p1 is 58.13 degrees and theta p2 is basically 148.13 degrees. Okay, now next thing comes maximum in plane shear. Okay, so what is maximum in plane shear? Maximum in plane shear is basically that particular quantity of tau at a particular orientation in which it is having maximum value. Okay, maximum in plane shear. Okay, so basically that value of tau xy which is maximum of this. Okay, so how to calculate it? This is basically equal to r value. Okay, how it is r value you will get to know in subsequent class, or even I will explain it when the particular concept comes, but because it is in the problem of here, I will just write for now. So maximum in plane shear is basically the radius r as in this value of r. Okay, which is equal to 30.06 MPa. Okay, and orientations is basically calculated as theta s, which is equal to why it is like this we will get to know after we understand the concept of Mohr circle. Just because these questions are there, I am implementing it, but we will understand this very carefully, very clearly, and actually these concepts come. Explaining this now will just create confusion. Okay, so theta p plus minus 45 degrees. So when you just put, now it's just the putting values. So when you will put values, you will get one orientation 13.13 degrees and the second is 103.13 degrees. In one way I can explain, let us suppose again you go from theta 0, 1, 2, 3, 4 till 360 degree, actually calculate the value of sigma x, sigma y and tau xy. You will get the value of tau maximum 2 times, as in all the way, the maximum all the complete column will get 2 times, and when you will calculate the orientations, this will be the particular orientations at which these happen. Okay, so that is the only mathematical way or just the engineering way I can explain you for now and as a hands off. Okay, fine. So we understood maximum in plane shear and its orientations also, something new in this problem. Okay, fine. Let's move to the next question now. Okay, so sigma y is given to us, tau xy is given to us, sigma 1 is given to us. Okay, we need to calculate sigma x, sigma 2, principal directions, maximum in plane shear again came into picture, normal stress on maximum in plane shear plane, something new, and the stress state at theta is equal to 25 degrees. Okay, so please at least try solving it so that it's clear that you are actually getting it. Your concept regarding sigma average will now come into picture. But please understand this now. Don't understand it in the previous steps. When you will understand normal stress on maximum shear planes, your concept of sigma average will come into picture. But understand that it is just a simple one case at which this is happening. It cannot be always, and we cannot generalize this. I will explain this. Please try solving it. So you know the value of you know sigma y. You know the value of tau xy. You know the value of sigma y. Only thing which you don't know is sigma x. Okay, so it's one equation, one unknown. When you will solve this, you can simply get the value of sigma x as nothing but equal to 70 MPa. Okay, so that is regarding sigma x. Now for sigma 2, what we can do, we can just again use our invariance concept. When you will calculate using invariance, you can get the value of sigma 2 as minus 50 MPa. Okay, this is minus 50 MPa. Next is regarding the principal directions. So we can use tan 2 theta p. Using tan 2 theta p, you can get the value of theta p1 and theta p2. So theta p1 is nothing but 26.565 degrees and theta p2 is 116.565 degrees. Okay, now comes the next part. Next part is regarding principal maximum in plane shear. In the previous question only we understood maximum in plane shear is nothing but tau max, which is equal to the R value. R value is again root over sigma x minus sigma y by 2 whole square plus tau x y square. When you will calculate it, you will get the value as 75 MPa. Okay, that tau max. Fine, this is tau max. Now, normal stress on maximum shear planes is basically the value is calculated as sigma average. So when you will actually calculate the normal stress on maximum shear planes, how it is calculated we'll get to know in subsequent weeks. But now, for now, normal stress on maximum shear plane is basically sigma average. So this is a particular case in which we get the value of sigma average. But we cannot in initial sense generalize it. Okay, so normal stress on maximum shear plane is sigma average. Let's use it in some essence. Okay, this is just a case. This is just the terminology which is being implemented. So normal stress. So what will actually be happening up here? Let us suppose we are on this substance up here. This is your sigma x, let us suppose. This is your sigma y, let us suppose. And this is your tau x, let us suppose. Okay, so at a particular orientation, at some particular orientation, let's say theta, this tau max, this tau will be maximum value. This tau will be tau max. And at the particular orientation of this tau max, the sigma which is being acted outside is basically the value of normal stress which we are calculating. Okay. So therefore, normal stress on those planes is basically equal to sigma 10, which is equal to sigma average, which is equal to 25 MPa. Okay. And the last question answer, what is the stress at theta 35 degree? Okay, so this is nothing, this is just the formula putting question in which you will just put theta 25 degree in sigma x dash is equal to formula, sigma y dash equal to formula, and tau x dash y dash equal to formula. Okay, so I've just added all these things so that your at least you try solving all these questions, so that at least there is no calculation error when you try to solve these questions. So it is 99.89 MPa. Sigma y dash at theta equal 25 degree is minus 49.89 MPa, and sigma x dash y dash is basically 4.10 MPa. Okay, so that was a complete question. The only new thing which came in this question was normal stress on those plane, which is basically sigma n is basically equal to sigma average. Okay. First, let us solve this question. Okay, because FAB is similar only. I need to explain different concepts to you. Please try to solve this question once. So basically, stress tensor is given to you. Stress tensor. Okay, there is stress is basically a tensor of second order. Okay, so sigma is basically denoted as 96 minus 72 minus 72 24. Okay, now please try to solve the first question. They are trying to say that find principal stresses from delta equal to sigma minus lambda I equal to 0. Sorry, not delta, sorry, determinant. Okay, so please use determinant and find out the characteristic equation, and using the characteristic equation try to find out the value of lambda. The value of lambda which you get is basically the principal stresses. So this is also one of the way in which the principal stresses are being obtained. Okay, so please solve this question. Okay, this is a very interesting question, that's why I have put it up here. Please try to solve this question. We'll put some time into this question. Okay, so when you will do determinant of sigma minus lambda I for this, you will get 96 minus lambda minus 72 minus 72, 24 minus lambda, determinant of this equal to 0. Now when you will solve this, you will get a characteristic equation of lambda square minus 120 lambda minus 2880 equal to 0. And you will solve this, the quadratic equation, you will get two different values, that is 140.50 ampere and second is minus 20.50 ampere. These two different values or these different eigenvalues are basically your sigma 1 and sigma 2. Okay, so sigma 1 is basically 140.50 ampere and sigma 2 is basically minus 20.50 ampere. Okay, this is the first concept. Second concept is regarding normalized eigenvectors, principal angles. Okay, so eigenvectors here are basically a direction vectors. Okay, so let's say if I write this as v1, v1 is basically cos theta sin theta. Okay, and what is v2? v2 is basically minus sin theta cos theta. Okay, so now when you will basically use eigenvectors with this, you can get, or in another sense, you can get theta p1 and theta p2. So theta p1 is basically minus 31.72 degrees and theta p2 is basically 58.28 degrees. Okay, and the third thing which I need to explain to you is regarding orthogonality. Okay, so I will just explain a little in brief what is the meaning. Verify that the transform tensor is diagonal. Okay, so for this orthogonality, so these all things are basic concepts of matrices. Okay, so that's why all the mathematical things I am avoiding in this lecture. I'm trying to explain all of those things which are related to mechanics of solids. Okay, so orthogonality and diagonalization. So basically from this we can actually know, so diagonalization basically means that when you try to transform the equation, the value of basically q transpose dot sigma dot q is basically equal to principal stresses. Okay, if we are trying to find that, then it is orthogonal. Basically the transform tensor is diagonal. Okay, so this is basically telling us that q transpose into sigma into q is basically what, if you can calculate it. Okay, so what is q up here? Q is basically v1 v2. Okay, so when you will solve this question mark comes out to be 140.50 minus 20.5. Okay, so that is the meaning that, okay, yeah, so q transpose sigma q works up here also. Okay, so the basic meaning, let's not go into very deep detailing of mathematics up here. The first reason we need to understand it, let's say if we have sigma stress tensor given to us, we can actually calculate the value of lambda, sorry, we can actually calculate the value of principal stresses using eigenvalues also. So if you can actually calculate eigenvalues, you can actually calculate the value of sigma 1 and sigma 2. Eigenvectors are basically v1 and v2, which are basically direction angles, and that can actually be used to calculate the value of principal angles. Okay, and the third thing was regarding diagonalization. Okay, fine. So that was this thing. Rest questions, I think, there are, in every question there is something new. Inferential orientation is being done. Fine. So let's do one more question and then we can end this session. Okay. So please try to solve this question. Just for a quick revision, so that we are actually clear with all the concepts which we are trying to understand. So let us suppose that there was some sigma. This is some square. I will make a big square which is having some delta A. The stress which was being acted upon in this direction was basically called as sigma x. The stresses which was actually acting in this direction was called as sigma y. The shear stress which is being denoted like this is in this direction. In this direction, this is denoted as positive, is tau xy. Okay. Now, when you will try to rotate this, you will get different values of sigma x dash, sigma y dash, and tau x dash y dash. I hope that thing is clear. As simple, if you try to rotate it, you will get different values of stresses. Okay. There are some instances, as in some values of theta, at which you will get sigma x as sigma 1, sigma y as sigma 2. Okay, we are denoting that as theta p1. Similarly, you will get somewhere some value of theta at which you will get this value as sigma 2, this value as sigma 1. We are denoting that to be 2 theta p, theta p2. Okay, first thing. Again, next thing is we found that theta p1 and theta p2 are basically interrelated to each other. Fine. Second thing. Third thing is always sigma 1 is greater than sigma 2. Always sigma 1 is greater than sigma 2 on number line. Fourth concept is regarding shear stresses. So again, when you will increase theta, there will be one theta at which the value of tau xy will be maximum. That is basically called as tau max. The orientation is basically called as theta s. There is relation between theta s and theta p also. That is theta s is equal to theta p plus minus 45 degrees. Okay. What thing more can be understood from this? Yeah. Now, at the particular orientation, when the value of theta is equal to theta s, tau is okay. Tau x dash y dash basically becomes tau max. But what actually happens to sigma x and sigma y dash? That sigma x is basically normal stress. Okay, so that normal stress value is basically equal. So basically at uh, uh, at tau x dash y dash equal to tau max, you will get some value of sigma x dash. That sigma x dash is basically equal to sigma y dash is basically equal to sigma x plus sigma y by 2. Okay, so this is the fifth point, I think, which we understood, right? So I think, yeah, so these were the major things which we understood from this chapter, from this lecture. Okay, so I can just keep it for the future reference. This is just as a revision part. Okay, you can just ignore it. Please just solve this question and then we can end this session. At least calculate sigma y, tau xy. So whenever sigma n is given, sigma n can be assumed to be sigma x only. Here sigma n is basically sigma x. Tau nt is basically tau x dash y dash at that particular point. Okay, so tau sigma n is sigma x dash and tau nt is basically tau x dash y dash. So how to solve this? I will just start a little. Sigma x dash is given to you. So sigma x dash, we know what is sigma x dash. Sigma x dash is nothing but sigma average plus d cos 2 theta plus tau xy. So sine 2 theta. Okay, we know the value of tau xy, we know the value of in these terms we know the value of sigma x dash and sigma x, so it just sigma, you need to know sigma y dash. So when you will calculate sigma y dash, you can get the value as equal to 151.00 MPa. Okay, we need to use another equation also of tau xy for this, that is minus d sine 2 theta plus tau xy cos 2 theta. I will just put that here also so as to avoid confusion. You need to use tau x dash y dash is equal to minus d sine 2 theta plus tau xy cos 2 theta. Okay, so now two equation, two unknowns will give us sigma y as approximately equal to 151 MPa and tau xy is basically approximately equal to minus 0.206 MPa. It's not zero, it's approximately zero. Okay, so therefore we can assume these to be approximately principal stresses, sorry. But even if that is not the sequence, we will actually calculate what is the value. So we'll just put sigma x, sigma y and tau xy is known to us. You can actually calculate sigma x is equal to sigma average plus r, and sigma 1 is basically sigma average plus r, and sigma 2 is basically sigma average minus r. So when you will calculate it, you will get the sigma 1 value as, again, it's 151.001 MPa, and sigma 2 is basically 89.999 MPa. Okay, using this you can get theta p1, theta p2. I hope now the actual essence of theta p1 and theta p2 is clear to you. So it is minus 89.81 degrees. In another equivalent form, we can add this also to be equal to 90.19 degrees. Okay, by adding 180 degree into it, and similarly 0.19 degrees is theta p2. Okay, what is more asked up here? Maximum in plane shear stress. Okay, so maximum in plane shear stress is tau max. Tau max is, we know, that is nothing but equal to r. R value is approximately equal to 30.50 MPa. Okay, then for the next thing, let me add a page up here. And the final thing which is being asked is stresses on the perpendicular plane and traction magnitude on the original x face. Okay, so the plane which is perpendicular to this, which is perpendicular to theta is equal to 40 degree, will be at 90 degree angle to it. Okay, on the plane which is perpendicular to this, which is 90, which will be oriented at 90 degree, so it is total oriented at 130 degrees. Okay, so sigma n at theta is equal to 130 degree can be calculated as 126 MPa. Similarly, tau at the particular portion is nothing but equal to minus 30 MPa. I'm leaving the calculations up to you. Please try to solve this and actually at least match the solution so that you are clear. Okay, you can understand the question, you can apply the logics, and you can get the results. Okay, and finally, traction magnitude is nothing but in along that direction. Okay, so it's nothing but equal to root over sigma n square, sigma x square plus tau x square. So when you solve this, you will get the value as 90 MPa. Okay, fine. So that is how this question is being solved up here. Okay, so I just explained this so that I can explain, okay, that the values can be approximately zero also, and even then sigma 1 and sigma 2 are a little bit different. Okay, so that was the basic meaning of adding this question up here. Okay, fine. So let me stop here only. You can try solving these questions, or else if the time persists, we can even solve this in the next class if there is nothing major contribution of the next week, or else you can please try solving this question. These are all based upon shear stresses, normal stresses, all these things only. Okay, Please try to solve this one. These are very good question. Everything has something new in it. Fine. So that thing being said, let me stop the lecture here. Thank you so much.